So the next thing that we are going to talk about in terms of convolution is the continuous time signals in systems. So far we have been talking about convolution sum. Let's take a look at convolution integral. And in order to motivate convolution integral, let's talk about response of LTI systems and how we would tackle that for continuous time domain. A lot of the principles that we learned for the response of LTI system for discrete are going to map directly to continuous time. We began with the impulse response, and that's exactly where we will begin with the continuous time conversation. So we'll start with finding out the characteristics of an LTI system by sending in an impulse delta of t and measuring or recording the impulse response h of t. So on the left we have the impulse, which is our input, and on the right you would get the impulse response. And once you have this impulse response, you have essentially characterized the LTI system. And once you characterize the LTI system, you can send in any arbitrary input and determine the output of that LTI system, because we already know the impulse response of that system. So first find out the properties of the system, then use that to find out the output for any given input. Now the question is, how is the output y of t related to x of t and h of t, the impulse response and the input? So how do we find that out? So to find that out, we will go through a list of operations that we will do first with the impulse response itself. We defined the impulse response of the system as the output of the system when the input is delta of t. So impulse goes in, impulse response comes out. When we multiply the input by some scalar, say k is a scalar, when you multiply the input, and the fact that we know this is linear and time invariant, so if it is linear and time invariant, it has to be linear. When it is linear, it has to be homogeneous and additive. So if k is a scalar, by using the homogeneity property, I can multiply the input by k, and if I do that through the system operator, I also multiply the output by the same scalar k. Make the input bigger 5 times, the output also gets bigger 5 times. Right? That's homogeneity. And we can do that because we have assumed a linear time invariant system, specifically a homogeneous system. How about when we delay, I should say shift? When I multiplied by k, I multiply by k. And because our system is time invariant, when I shift by tau, I also shift the output by tau, because the system is time invariant. Next, can I say that k is a scalar, so some value, and if x of t is like that, what is x of tau? This is t, this is x of t, this is x of t, and I evaluate x of t at some tau. So I'm saying that tau is some constant. What would be the value of this be? It would be x of tau. And I'm using that as k here, some value. X of tau is evaluating x of t at time tau, and that is my x. That is my k. So I'm essentially changing my scalar to value of x of t evaluated at some time tau. And because I do that, I also do the same scalar at the output side. So I've essentially set k as x of tau to go from here to here. And these are the same system operator here, here, here as well. Now I integrate both sides. Integrate. Why can I integrate? Anyone? Why can I integrate input and also claim that it will be an integration of the output? The reason for that is superposition. Superposition is if you scale and shift multiple inputs, the output will be the scaled and shifted versions of their corresponding outputs. So if I integrate everything on the left side, it will be an integration on the output side as well. So I essentially add up the two integration signs here and here. Now I want you guys to notice what this is. The thing in the box. By using sampling property that we discussed in the previous lectures, I can say that that is essentially x of t. So this is saying that if the input is x of t, the output will be an integration of x of tau h of t minus tau d tau. Very similar to the convolution sum. The changes are summation has been changed to integration. Tau has been small m has changed to tau, and small n has changed to t. And you get the convolution integral to find out the output of an LTI system, continuous time. All right, let's move on here. So that's essentially the convolution integral. If you have an input x of t, you can find out the output of that system, LTI system, y of t, by evaluating that convolution integral. It is going to be very similar as the steps that we followed in the continuous time, at least when we are talking about the graphical approach. In the graphical approach, what did we do? We fixed one signal, the other signal, we flipped it, and then we moved it across the other one. And while we were doing that, we were multiplying the signals and adding up all the common elements. In this case, we would keep multiplying the two signals and we would integrate over the overlapping time instead. So we'll go through some examples to talk more in detail about that. So this integral over here is the convolution integral, and it integrates the convolution between x and h. They are both continuous time, and we are still again using the asterisk sign to denote convolution operator. Let me take a moment here to see if you guys have any questions. All right, I see that you guys are saying that it is a bit laggy with respect to the laser pointer. So I'm going to try to walk through these steps a little bit slowly, at least with respect to my usual speed. But at any point, if you feel like it is going a bit too fast, please let me know and we can retrace our paths. We had three ways to evaluate the convolution sum. We do not have an array algorithm that we can take advantage of in convolution integral. We can still do it analytically and we can still do it graphically. So let's take a look at both these approaches to find out the convolution integral. The first example we will do is a simple one. Here we are trying to convolve x of t and h of t. X of t is given to us as t times u of t, which is essentially the ramp function there, r of t. And our, well, this needs to be corrected here. This is h. H of t is also r of t. So the two continuous time signals that I'm trying to convolve here are x of t and h of t. Both are given to me. They are r of t, which is time less than 0, it is 0. Time greater than 0, it is t. Equal to 0 when time is less than 0, equal to t when time is greater than or equal to 0. All right, let's start with the convolution. This is the analytical approach. So let's do this. I will do this in red. So I will say x of t convolve with h of t equals integration negative infinity to infinity. I've got x of tau multiplied by h of t minus tau d tau. And in this case, both x and h are the same. So it doesn't really matter which one I consider as tau and t minus tau. So which one I consider as x and h doesn't really matter. Notice again, it is commutative, so it doesn't really matter which you convolve with what. There's no first and second, and we will prove this later on. So you can do it based on what is convenient, and when we go through the examples, you will see what is convenient and what is not. All right, let's see. What is x of tau? X of tau is simply tau. X of t is t. So x of tau should be tau. We will adjust the limits of the integration later on. But right now I'm just substituting for x of tau here. Next, I have h of t minus tau. H of t minus tau would be t minus tau. Oh, sorry, this needs to be u of t. U of tau. T minus tau, u of t minus tau, d tau. All right, this is shaded in blue for that, and then this shades in pink for that. Next, we note that u of tau is going to be 0 when tau is less than 0. That's the definition of unit step. We need that piece so that we can leverage that over here in order to adjust the limits on the integration. Also, u of t minus tau is going to be 0 when tau is greater than t. So if the argument inside the function is negative, it is 0. It is negative when tau is greater than t. Let's see. By using these two things, we know that there is not going to be any overlapping region when you multiply these two signals below 0 and above t. Below 0 because of this, and above t because of this. So I can adjust my integration limits to 0 to t by using the unit steps. I'm left to, and then now inside that time 0 to t, u of tau and u of t minus tau both are 1. So I don't even need to write those. I simply have tau multiplied by t minus tau d tau. Now I can actually go through this integration. So I have, let's see, t tau squared divided by 2, and then you have tau cubed divided by 3, and then the limits on that would be 0 to t, and this is only going to be valid between time greater than 0, so I need to multiply that with u of t there. I've also put in the limit, so it's simply the integration. If you solve this integration, you will get t cubed divided by 6 u of t. So the analytical approach is a direct substitution of x and h, or the two signals, and then taking a look at the properties of the signals themselves to adjust the limits on the integration, and then actually doing the integration, substituting the limits. Now this is really good as far as some standard signals are concerned. So for example, u of t, right? We were able to leverage the fact that it was u of t. Sometimes you might have an exponential signal. So going from 0 to infinity, for example, and things might cancel out. You might be able to do the integration and you might be able to express the answer very easily. But in some certain cases where the shape of the signal is kind of changing multiple times, like it is it's constant for some time, then it linearly increases for some time, and then it linearly decreases for some time, and so on, you might have a tough time doing an analytical approach, because the number of terms you would have to manipulate will be too many. So for those kind of cases, a graphical approach is much better. And the principles of the graphical approach are very similar to the discrete time conversation. It will involve changing the variables, it will involve flipping things about the y-axis, it will involve moving things from left to right, and as you do so, you will multiply the signals and then integrate over the overlapping region. And we will do all of that today. So there is a question on the chat box about whether we can do the previous example using r of t instead of tau u of t. You meant t u of t. Yes, there is. But then when you start doing r of t, it is by definition t u of t. So you might have to keep track of the time limits slightly in a different manner, but they are both effectively the same signal. So you could do either way. All right, coming back to this. Over here, we are going to go through this graphical approach. We are given two signals, f of t and g of t. F of t is a very innocent looking rectangular pulse from -1 to 1. G of t is a linearly increasing function, and then it instantly drops from 1 to 0 at time 3. Both are continuous time. Both are defined with respect to a time variable small t. The steps that are involved in this convolution, the convolution that we are going to do between f and g, involves g of tau So in order to find g of tau, you would have to plot g of tau, because right now we are doing graphical approach. Next, we would also need to do f of t minus tau. So you start with f of tau, then you flip it, you get f of minus tau, then you add t to it. So you sketch f of t minus tau. Then you multiply the two signals because you are multiplying there. And then once you multiply, you integrate over all that overlapping region. So find the integral of the product signal with respect to the independent variable tau. Over here, the independent variable is the tau. This, the next example that we are going to do, I encourage you guys to follow along really well, because this conversation will help you with convolution to a very great extent. So let's do this step by step. The first step is to plot g of tau and f of t minus tau. These steps were laid out in the previous slide. Plot g of tau. Okay, I know g of t, so plotting g of tau should be very straightforward. G of t is linearly increasing from 0 to 3. So g of tau should also linearly increase from 0 to 3. So I have tau here now, and I have g of tau here. And then in say I'm using blue for g, so I'll just use blue there. 0 goes to 1, comes down, stays there. Nothing really changes except for the fact that we changed t to tau. Next, f of t minus tau. So I will do this in a few steps here. So the first step is going to be this. I will use this as my intermediate axis. First I go to tau. This is going to be as straightforward as simply saying this will be doing the same as before, except the limits 1, 0, -1, this is also 1. That's f of tau. Next, I need f of minus tau. Well, if I flip it about the y-axis, it remains the same. So I can, without any problem, I can add a minus there and it is the same. How about the next step? T minus tau. What about that? I need to add t to my time axis as well as the function. So this becomes t minus tau, this becomes t plus 1, this becomes t minus 1, and this becomes a t. So I have added t to all those times. So that's essentially going to be my signal here. So I have that, and that, 0 there, 0 there. Next, this is going to be f of t minus tau. This is tau. This is t plus 1. This is not 0 anymore. This is t, and this is t minus 1. Now, I like to think of this t as a set of wheels. The set of wheels that this signal f of t minus tau is on. And those set of wheels will allow this rectangle to move from left to right. And as you are changing that, moving that from left to right, you're essentially incrementing t. So we are ready with g of tau and f of t minus tau now. Now the next question is, because we are interested in multiplying the signals and integrating the overlapping region, I can evaluate this overlap in multiple cases. So the first case that I'm going to consider is when t plus 1 is less than 0. When t plus 1 is less than 0, there is no overlap in those signals. Let me show you that over here. So what I'll do is I will copy this one, paste it here, but I'm going to paste it slightly in this direction there. And then I can bring in the other guy and paste it over here. So my g of tau is fixed, but f of t minus tau, after it gets flipped, it's now moving across g of tau. So this is the product now. So this is g of tau multiplied by f of t minus tau here. This axis is tau. The height is 1 for both of them. Now as you can see, that point right there was t plus 1. And when t plus 1 is less than 0, there is no overlap between those signals. So case 1, I will define case 1 as t plus 1 less than 0, which implies t is less than negative 1. When t is less than negative 1, what do you have for y of f of t convolved with g of t? Is 0, because there is no overlap. By the way, when t minus 1 is going to be greater than 3, there is also going to be no overlap, and that's also when you will get a 0 convolution result. We will see that in the last case. So we are essentially moving that red signal f of t minus tau from left to right now. Let me erase this, and then, so what would be the next case be? The next case would be when this comes inside, right? So it's still here. So I'm going to copy this from here. I'm going to go to the next slide, paste it, and adjust things slightly. So this was earlier. I'm going to next, let's see. That's my next piece. And what is going to be the case here? The width of this, I'm showing a little bit broader here, but if you consider the width here, it is 2, because negative 1 to 1, and the width over here is 3. So this rectangle can completely go inside the triangle, but that's not happening right now. It is on the way in. So right now our time is t plus 1 is greater than 0, but for how long will that increment? In other words, as you are moving things from left to right, that t plus 1 value, when it is greater than 0, you will start overlapping, you will start having some overlapping region. And that overlapping region, which I'm going to essentially, let's shade this here, shade it. That overlapping region will continue to increase. But until what time will that continue to increase? It is going to continue to increase until the entire signal goes inside that triangle. So for about 2 seconds, it will continue to increase. So let's see, which can be written as t plus 1 has to be greater than 0, which implies t is greater than -1 for 2 seconds, right? So for 2 seconds, which implies that t also has to be less than 1. So to combine both of them into one condition, you have -1 less than t less than 1. And in that particular case, you are multiplying the two signals and you are integrating over the overlapping region. So how does that look like? Let's see here. Yes, and black. The convolution result f convolve with g can be written as, what would be the limits of that integration? So Jason says 0 less than t plus 1 less than 3. No, it would be not 3, Jason. The upper limit would be 2, because the rectangle is narrower than the triangle. So what would be the integration limits be? Well, you would have to take a look at the overlapping region. The overlapping region suggests that the lower limit on the integration is 0, and the upper limit on that integration is t plus 1. That's when you have the overlapping region. So let's do that. I have black here. So 0 to t plus 1. I'm multiplying 1 with what? Because this is the red one, the red signal f of t minus 1 is 1. So I'm multiplying 1 with a triangle here. So I would need the equation of that line. Passes through 0. So that's fine. Passes through 0. So there's no y-intercept. What is the slope? The slope is 1/3. So this would be tau divided by 3. That's g of tau. G of tau between 0 and 3 is tau divided by 3. So I would need to write 1 multiplied by tau divided by 3 d tau. That would be my convolution result. So do the convolution, you get tau squared divided by 6 here, and then the limits on tau would be 0 to t plus 1, and you can substitute easily. You get what? T plus 1 squared divided by 6. That's it. So the convolution result between -1 and 1 second is tau squared, t plus 1 squared divided by 6. All right. Next, let us move to case 2. Sorry, case 3. What is case 3? Let me draw the two signals here. Perhaps I can sketch them in a slightly better manner. Blue goes from 0 to 3 there. Right. So it is the time when the rectangle is completely inside the triangle. What are the limits? This is t plus 1. This is t minus 1. This is 3. But the overlapping region is what matters. So the overlapping region is right there. Maybe I should sketch it slightly. So I need to multiply them again and integrate. The height is 1. For how long will that last? That will last for just 1 second. Because the width of the triangle, the difference is 2 and 3. So this will go from 1 to essentially 2. What would be the convolution here? Limits on the integration will be t minus 1 to t plus 1, corresponding to that and that. And then one of the signals is 1, the other signal is tau divided by 3 d tau. Simplify tau squared divided by 6. Substitute limits t plus 1, t minus 1. Simplify, you get, let's see, t plus 1 squared minus t minus 1 squared divided by 6 to t divided by 3. Yes, 1 less than t less than 2. You're right. Again, this is tau. This is f of t minus tau multiplied by g of tau. All right, we are moving ahead. Keep moving the right signal in the red to the right. Case 4. Case 4 similarly would be when my first I will start with the blue. Then I will put in the red. Now my integration will be over here. The time limits will be, this guy is 3. This guy was what? T minus 1. That is t plus 1. But the overlapping region is from t minus 1 to 3. What would that be for? It will be for 2 seconds. 2 less than t less than 4. F convolved with g is going to equal integration from t minus 1 to 3, corresponding to that limit there and that limit there, followed by 1 multiplied by tau divided by 3 d tau. And if you plug in the numbers, evaluate, simplify, I'm just going to write the result here. T squared minus 2t minus 8 divided by 6. And then the last case would be when the red rectangle exits out of that blue. Let me start with blue again. And then the red guy will be over here. And let's write the time marks here. This is 3, this is t minus 1. So when t minus 1 is greater than 3, which implies t is greater than 4, you have no overlapping, so you get 0. All right, so you can write out the convolution result, all of that result in a bracket notation now. All you have to do is combine all the 5 cases, express the convolution result in a bracket notation, and that will be it. All right, questions about this example here? So I'm essentially going to, could you go over case 4 again? Yes. So case 4 is when the red rectangle is on its way out of the blue triangle, and this is when t minus 1 is less than 3 and t plus 1 is greater than 3. So it's by combining those two statements, you can write 2 less than t less than 4 for the time, and at those places you are essentially multiplying 1 here, f of t minus tau is 1 there, with tau divided by 3, which is g of tau, which is the equation of this line. So, all right, another way of looking at this is this, right? So you're saying that t minus 1 is less than 3, and you're also saying that t plus 1 is greater than 3. And when you combine these two, you get that. All right, other questions? All right, let's see here. Done with this. Okay, so I don't think we have much time here, but I will walk through perhaps one example and then we can stop there. We did this. Let's see, what example do I want to walk over? This one. So this is a similar continuous time convolution example. In this case, you have two signals that you're trying to convolve. One of them is u of t. The other one is u of t minus u of t minus 1. So actually, I can refer to this as simply g of t, the gate function, which looks like that, 0, 1. This is g of t. Open the gate at 0, close the gate at 1. Next, I'm going to try to see, let's sketch u of tau. So fix one. Which one should I fix? Well, this one goes on to infinity on the right. This one is limited. G of t is limited. So I will fix u of t, and I will flip and slide g of t. I think that will be much easier. So if I have to fix u of t, what do I need to do? First, I need to write the integral. Y of t equals integration u of tau g of t minus tau d tau. So let's try to sketch u of tau first. On the right, I have 0 here, then I have 1 there, and I have continues to be a 1 there. This is going to be u of tau. This is going to be tau. This is 0. All right, so I have changed the time variable from t to tau, and I have fixed that. This is fixed. I'm not moving this. The next piece I need is g of t minus tau. So what would be g of t minus tau? Let me draw g of t minus tau right here. This needs to be g of t minus tau. That needs to go. All right. Now, instead of doing this in multiple steps, let me just do this as g of t minus tau. I have already changed the time variable over here to tau, and I will consider the first case where there is no overlap. So when I flip this, what happens? When I flip this, it will become that, and this will be 0, this will be minus 1. When I do t minus tau, this will become t minus 1, and then this will become t. So I'll just use that instead. Let's see here, red, there. The limits, this was t, this was t minus 1, and that height is still 1. All right, so case 1, what would case 1 be? Case 1 would be when t is less than 0. When t is less than 0, you have no overlap. How about case 2? It is starting to go in. All right, so let's move it in and see what happens. I'm going to move this over here and also move this over here. Where is the overlapping region? It is going to be over here. Limits should be adjusted to 0 to t. And it is only going to do this as long as t is less than 1, because if it's t is less than 1, then the g of t will be completely inside the unit step. After that, it will follow one behavior. So this is only going to be for 0 less than t less than 1, only for one time step, where y of t is integration from 0 to t. Those are the limits on the integration. That's where the overlap is. And we are multiplying 1 with 1, d tau. both u of tau and g of t minus tau are 1 there. So you get t there. Linearly increases. What about case 3? Case 3 is going to be when it is completely inside, right? So that's when it is going to be, let's see if I can perhaps change this. The overlapping region now will be all of the inside, because all of that overlaps with that. What are we integrating here? Y of t is going to be integration t minus 1 to t 1 times 1 d tau. Well, that's just simply 1, because the area of that rectangle for one time step. So we got 3 results here. Let me box them up. 0 there, t there, and 1 there. This will allow us to sketch y of t. And let's see, I will use blue for the output here. Linearly increases for one time step and then stays there. This is going to be y of t. This is t. This is 1. This is 0. This is also 1. Done. So as it is moving inside, linearly increases for some time, because 1 times 1, and then after it goes completely inside the unit step, it stays at 1. All right, let's stop over here, and then we'll pick it up with more examples and more properties of convolution in the next one.